Hello, this is Bob Vrabel again from TAE Aerospace, coming to you for another IA renewal seminar. I'd like to thank Concord Battery and Virtualis Live for their work on bringing this to you and helping me to bring you another saga of the TPE331. Again, I represent TAE Aerospace. This is a brief history for those that haven't seen my presentations before. The TAE Aerospace is an aerospace and defense firm based out of Adelaide, Australia, with offices worldwide. I am based out of the operation out of Scottsdale Air Park in Scottsdale, Arizona. What was once, for those that may remember, Copper State Turbine Engine Company, CTEC, or Executive Aircraft Maintenance, EAM. TAE had acquired those. Predominantly, I also work out of the Scottsdale area. Our primary functions there are major engine repair, major MROs on on the Honeywell TPE331 family of engines. In addition, we offer a full line of TPE331 component repair and overhaul. Also field testing and repair, part sales service, the usual with that. Technical training, which is my primary function. I am the training coordinator and primary instructor for TAE Aerospace, based out of the Scottsdale operation, which is where we have our in-house training facility. Although we also do training worldwide at your facility if you choose to do that. You can find out more about the services that we have available if you want by going to www.taeaerospace.com under the Contact Us tab. And you can that would lead you to your local sales reps for whatever region that you're located at. And also looking at some of our capabilities if you're interested in receiving more information on that. In addition, as I said, I'm the training coordinator and primary instructor. You can see the information there is how to be able to reach me if you have training needs or are interested in learning more about our training capabilities. I would be more than happy to contact you, provide you with training quotes, etc. Large groups of technicians to be trained. I think I would recommend taking advantage of our flat rate pricing that we usually do up to 6 technicians or mechanics or engineers for the same flat rate price. And if you're interested in something like that, again, there is my email, or you can call me directly at that phone number, and we can talk about what your training needs are. The facility itself, as you can see, is located in Scottsdale. In addition, we also have PT6 overhaul facility located in Eloy, Arizona, just south of Phoenix, between Phoenix and Tucson, that provides the same services that we do on the TPE331 for the PT6. And so again, contact www.taeaerospace or contact the phone number you saw previously, the phone number 480-500-6677, to be connected with someone that would be able to help you with your PT6 needs as well. Now, for this presentation, what I'd like to talk with you guys about is a basic fuel system troubleshooting. Now, we cover this in much greater detail in my training classes. So what we're going to do is we're going to dip a shallow end, our toe into the shallow end of the pool on this one, talk about just some basics and some recommendations. Most of the troubleshooting, some of you guys are probably well versed in, but hopefully we might show you a new wrinkle or two, even in the basics. So this is, you're probably not going to find a lot of meat on the bone, but hopefully maybe we'll show you a few new wrinkles on this. Now, with the 331, what we're going to be talking about predominantly is based upon the Woodward hydromechanical fuel control unit, which is the most prolific on the 331 family of engines. But these values, these pressures, etc., and techniques can also be used on the Bendix pneumatic fuel control variants of the TPE331, as well as the Honeywell electro pneumatic fuel controls themselves as well. So a couple of different operating functions, but and a couple of additional items to check for on the pneumatic and electro-pneumatic. But essentially, what we're about to present can be used as a baseline for even troubleshooting those particular model engines. Now, when a fuel system fails, or when a fuel system has a degradation, etc., there are a myriad of minor little symptoms and quirks and things of this nature. But under general circumstances, what you will typically find is that they'll manifest themselves usually for example, with a lack of lack of combustion would be one. A pilot or an operator would complain the engine did not combust, it did not light off. Can be one of the causes with a lack of fuel flow. Another is that if after combustion the engine is extremely slow to accelerate to a start condition or to a stable condition, or in some cases, the engine begins to accelerate and then stagnates, becomes a hung start. So this would be another general symptom. Also, temperatures, obviously, fuel flow on a gas turbine engine is going to have a direct effect on your indicated temperatures. So a restriction in fuel flow delivery would be a slow acceleration with cooler starting temperatures. A failure in which fuel flow is excessive would result in high starting temperatures with the potential to where the engine may have to be aborted to prevent the engine from going over maximum allowable starting limits. Another item could be unstable idle operation, that once you do get to a start condition, that the engine's ability to idle is compromised, either because of unstable fuel flow, the lack of fuel flow, so you're idling at the wrong RPM, too high, too low, whatever that may be. Another one would be that if you are, especially with the Woodward control, that a lot of this may also be difficult to accelerate from a low speed to a high speed, that when moving the cockpit control levers to demand a higher speed out of the engine, that the engine struggles to get up to that speed. Things like this would be much more visible to the operator or to the technician, especially in twin engine applications, in which when you move the levers simultaneously, one engine zips right up to where it belongs, the other one struggles to move along to try to get there. Then ultimately, this is probably one of the bigger complaints we have, is that the pilot would complain about the inability to make his expected output power for takeoff. So basically, we usually say he's low on power, he's not making his target torque or his expected value of output power. Now, on the other end, we talked about a lot of acceleration issues. Another one would be also, if I'm not getting enough fuel or I'm getting too much fuel through the scheduling and my fuel system, that is also going to affect my deceleration schedule, my deceleration rates, that the acceleration rate is exceptionally quick, or it's exceptionally slow, or I move the levers to a low speed command and the engine does not respond. With the fast acceleration, it could also result in a potential flameout. Taking too much fuel away drops you below your lean burnout characteristic, and the fire goes out. You can no longer sustain combustion. So these are some of a few of the generic reasons why you might have an issue or would need to troubleshoot the fuel system. Now, when I was a young instructor, and also a young technician, I was told that, and some of you may have already heard of this. If you've ever been to any of my classes, I try to introduce what I refer to as the big box theory. With the big box theory, this was introduced to me by a gentleman that basically, he says, okay, you've troubleshot the problem on your engine to the fuel system. So you know it's in the fuel system, which includes every and all component that's in the fuel system. So that's let's call it an 80,000 foot view of the fuel system. The big box theory is not designed to take you down necessarily to a specific component, but to deal with the fuel system in its big components. Now, we know that's made up of much smaller components, but this takes our view now. So I know it's in the fuel system. Now I want to narrow it down to where it's at in the fuel system. So I'm not going to a component just at this point. So I've got it. It's in the fuel system. I'm going to narrow it down to where in the fuel system, and then I will begin to dig deeply into all the components that occupy that particular area. Basically, this may have gone by different names, and you may have also employed this in your own troubleshooting when you take a look at the systems itself. So on the 331 family of engines, basically what we're looking at is that aircraft fuel is supplied to the fuel pump. From the fuel pump, pressurized fuel will be supplied to the fuel control unit. From the fuel control unit, fuel will then pass through the fuel shutoff valve and be delivered to the flow divider. Out of the flow divider, at the appropriate time, the fuel will then be delivered to your primary and your secondary fuel nozzles. So here we have the fuel system, not looking at the individual little tiny components, but as a set of boxes, the big box theory. All right. So now I know it's in the fuel system. Using this, I'm going to now narrow it down to where in the fuel system is, where I can then start to scrutinize the individual components themselves and all the different components that are associated with the fuel system as well. Now, one of the big things to be able to troubleshoot the fuel system is you're going to have to understand, where do I measure, okay? Like an electronics technician that has a default or faulty circuit, he's going to use his equipment and he's going to go along the circuit itself in an effort to try to identify where he has a good signal going in and a bad signal coming out. As engineers or as mechanics on ours, we do the same thing, but without all that equipment. We do it in a mechanical system by using gauges, all right? And so one of the most important items then is that, okay, where do I place the gauge to make the most effective evaluation of my fuel system? Well, obviously, we're going to try to measure at the outlet of each of the big boxes. So our first location is we want to try to put a gauge at the discharge of my fuel pump. Now, what I'm showing you here is my recommended. If you're going to try to put together a gauge kit or have gauges available to be able to troubleshoot the fuel system well, these are going to be the recommended pressure ranges that I would recommend you guys would get for your gauges. I'd also, I mean, they don't have to be laboratory quality, but make them sufficiently large enough to be able to be easily seen as you're potentially running the engine. It's also recommended that you don't use hoses that connect these gauges of more than 3 feet in length. You get an accumulator effect, which can trap fluid or trap whatever liquid you're measuring in those plumbing lines, which can also, make some interesting engine shutdown conditions, etc. And so we want to try to keep the lines long enough to where you can then route the gauge to an easily visible location, but short enough to where it doesn't start actually affecting the fluid dynamic. So there's your fuel pump. Now, on our 2 different styles of fuel pump, on the 300 series pump, you can see that on the top of the fuel pump itself, there will be a fitting. Now, this fitting in some cases will be predominantly used for the supply to our priming or our fuel enrichment equipment on the engine for engine starting. So this is a good location on the 300 series pump. There's an already existing fitting there. And so you don't have to go running around the hangar looking for AN fittings to be able to plug in to that particular location. And that's a 399 pump. On the 400 series pump, you can see a slightly different fuel filter and integration here. There is still our fitting on top of the pump, which offers an alternative where you could tap into that and read fuel pump discharge pressure. Or, as you see on this one, is an inlet up configuration style engine. On the fuel control unit, right just aft of the mating flange, there's a blue plug. That is actually tied into the fuel pump discharge coming into the fuel control unit. So, but here you can also see in this instance, you're going to have a fitting available, a separate fitting rather than a pre-installed fitting ready-made. But that is an alternative if you're interested in tapping in to that location as well. I have also used alternatives depending upon types of access. What you see represented here would be a style of priming circuit or priming equipment, what we call the start fuel enrichment or the start pressure regulator equipment that is used to add additional fuel to the engine during starting to make the engine start a little quicker. Now, the line you see coming in from the left over here, that is your supply line off the pump itself. And so if you want to have the ability to still start the engine to get up and look at higher values of flow and pressure to evaluate the system, you don't want to eliminate your start pressure regulator, or your SPR or your enrichment circuit. So here you could tap in, or if the engine physically will not start, this makes a readily locatable area to where you could disconnect this plumbing line and directly put a gauge in there and would be reading fuel pump discharge pressure. Now, if you want the engine to be able to start, I have used this technique myself And again, I offer this as an alternative to you. What you see below this is what's called the anti-ice lockout valve. It also receives fuel pump discharge pressure. This normally is going to be run through your fuel heater. So this is still the same pressure coming off of your pump. It is a normally open solenoid operated gate valve. So again, it has no regulatory feature whatsoever. And what I will do in some cases is that if I still need my SPR or my SFE, I will actually disconnect the plumbing line and cap it off, and will actually put a plumbing gauge or plumb a gauge in at the downstream side of the solenoid to prevent the valve from accidentally being energized during an engine start. I will then disconnect the electrical connector. It is a non-critical solenoid, so not having it operating is not going to endanger personnel or hazard the engine in any way. All right. So I offer this as an alternative, again, with a ready-made elbow to which you could then read pump discharge pressure. So several different alternatives to fuel pump discharge pressure. Here's an example of what we refer to as a start pressure regulator system. It does the same function. Most of the time, this type of system is manually operated by the pilot or the operator himself. Here again, if you're having trouble starting the engine or not getting the engine to start, you can tap off at this fitting that you see located right here, or the plumbing line, and actually read fuel pump discharge pressure here as well. And again, most aircraft installations, this area of the nose cone area is generally supplied with a removable piece of cowling, typically. So the access to this is generally not too distressful. Now, the next place we're going to want to look at putting a gauge, obviously, is at the discharge of the next big box, which is your fuel control unit. And again, guys, I know, yes, there are other components in between the FCU and the fuel shutoff valve, but again, we're trying to narrow it down to the area of the fuel system, not necessarily at this moment to a specific component. Again, about a 0 to 800 PSI gauge will handle the entire range of your fuel control discharge pressure ranges themselves. Now, where we typically measure this, what you may notice on your engine, you may already have pre-installed at the inlet of the fuel shutoff valve is a troubleshooting T. On early production engines, this was an elbow. There was not a T that was located here. And so to read this pressure, you typically had to then go and install an elbow, which luckily enough, a standard -4 T fitting, that when you put that in there, did not require a lot. It did not require any stressing or anything like that of the fuel supply line coming in. On later model engines, later production engines, say mid 80s and beyond, they started putting a permanent T fitting in here as part of the engine fuel system plumbing. So you already have a readily installed troubleshooting tap. On the earlier model engines, service bulletin incorporation was issued to be able, in a kit form, to be able to put a T fitting in to put a modified plumbing line, if necessary, into that location. I would recommend checking the front matter of your engine maintenance manual to see in chapter 73 in service bulletin 73 to see if there is a kit. If not, go ahead and you can contact companies like TAE, and they can do some research for you and find out whether there is a troubleshooting or a conversion, if you will, to where something like this could be readily installed and providing you with a permanent ability to be able to tap in and read those pressures. Now, for those that don't have a T fitting there, but they do have a limiter capability or a limiter installed, either a horsepower limiting system or a temperature limiting system or a horsepower and temperature limiting system, generally you're going to have a valve, what's called the horsepower limiter valve. On some applications, we refer to it mostly as the torque and temperature limiter bypass valve. This, wherever it's installed, sometimes on the side of the gearbox, sometimes on the back, one of the back accessory pads, there is a plumbing line that comes off of the discharge for the fuel control discharge, which will run into this valve. This valve is located physically between the fuel control and fuel shutoff valve. So there, especially if you're not intending on going up to very high powers or things like this, you could conceivably disconnect the plumbing line going into this valve and readily tap in and read your fuel control discharge pressure. So this offers you an alternative as opposed to if you don't have fittings readily available or one already installed at your fuel shutoff valve. Now, the next thing then across the next big box is to put a pressure gauge, again, in the discharge of the fuel shutoff valve or at the entrance to the flow divider, whichever way you want to term that. And again, you'll notice it's the same relative gauge range as your fuel control discharge pressure, because the fuel shutoff valve does not provide any kind of regulatory function. It's an open and closed ball valve. So I would expect 100% of the time that with a properly functioning fuel shutoff valve and no anomalies, that the fuel control discharge pressure and flow divider discharge pressure would be the same value. Now, that can be then installed. If you're looking at the yellow circle here, that is the entrance to the fuel shutoff valve, which leads through a self-bypassing screen. But this would be the location where you would install your gauge fitting. Again, on no application is there a T fitting in this particular location. So you would have to manufacture one and find some way to then connect the fuel supply line over to the flow divider itself. Next in line then would be our primary and our secondary supply lines. Both of these gauges basically would be the same gauge range. Now, depending upon your engine, on early production engines, T-fittings were not installed. So troubleshooting taps were not installed in the primary and secondary discharge. By the way, if you're interested, the primary is the small line. The secondary is the larger line. On early model engines, these were flex lines. And so there were no troubleshooting fittings unless there was a service bulletin that allowed for the conversion. But putting a troubleshooting T into that line was relatively easy because the flex lines were more giving of being rerouted or moved a little bit to be able to install a gauge. On later model at production engines, say about the mid-80s and beyond, they started putting hard T's into the lines themselves, basically permanent mounted troubleshooting taps to be able to measure your primary and your secondary pressures. So that would be an advantage with that. If you happen to have a later production engine that does not have the T's, but it has the hard lines, this is going to make it more difficult to be able to read your primary and secondary pressures because these lines would have to be put under some kind of stress to be able to install the T into there. It wouldn't be huge, but it would still be an amount of stress that would be involved with that. So take that into account when you're taking a look at your troubleshooting T's themselves. Now, once I've got the my gauge is installed, now I'm ready to do an engine ground run, and I'm now going to, like the electronics tech, I'm going to use my gauges to evaluate whether the system is functioning correctly by looking for expected pressures. And again, these pressures that I'm giving you can be found in your engine publications, either in 72-00-00 troubleshooting or 72-00-00 adjustment and test or testing. Up in the general section of the engine maintenance manual will be where you will find a lot of these numbers. I also put these out as standard issue when I do my training classes to make sure that when the technician or the mechanic or engineer walks out, they've got the normal. There's no way you're ever going to be able to evaluate a system as not functioning correctly unless you know what normal is. And so, so hopefully this will help you a little bit with some of the more generic pressures, etc. Now, coming out of the fuel pump, what I see here, what I would typically see, and what I'm giving you guys here is the pressures and temperatures starting at 10% RPM when the fuel shutoff valve opens. On all 331 engines, the fuel shutoff valve is commanded open, either manually by the pilot during a manual start or automatically by a speed switch. Through speed switch operation, fuel begins to flow to the engine. So I'm going to begin what you should begin to see at the moment fuel starts flowing to the engine, and then ultimately what it ends up with at the higher power, max speed, etc., what should be typically being now displaced out of the component at the higher power. So that, put that into your perspective, from 10% to max power or 10% to max speed would be what I'm about to give you guys. Now, what I expect to come out of the fuel pump starts at about 300 psi on initial fuel introduction, and then will ramp up ultimately to a maximum of 800 psi. Now, for those of you that were paying attention, you're saying, well, wait a minute, Bob, you want me to slap a 0 to 1500 psi gauge in there? That seems kind of like overkill for this area of if I'm only going to get about a peak of 800 psi. That's not necessarily so. Peak discharge pressures coming out of the pump can be anywhere between 1100 to 1500 psi when you slam the door when the fuel shutoff valve closes. So you want to have enough range on your gauges to be able to handle that spike in pressure without damaging a gauge. And so that's why I chose those particular ranges of pressure on your gauges, so that you don't wind up having a one-time use gauge. So nominally, I should see initial introduction of my fuel pump should start out at about 300 psi, and then we'll ramp up ultimately to about 800 psi at peak operating power. Now, when a fuel pump fails, in some cases, it may, if it's a total failure, I'm not going to get any starting whatsoever. So I'm not going to get up to a running situation to where I might be able to see some of these higher pressures. And so it becomes difficult then to sit there and say, well, I'm not getting, all you're going to get out of an engine starter, even with good batteries, is probably about 15 to 18% RPM. So you're not going to, you wouldn't expect to see these massive amounts of pressures. Nevertheless, there is still a normal pressure this engine pump should be pushing at the lower RPMs. Now, if you refer to chapter 720000 under troubleshooting, and depending upon which manual you're looking at, it will either be under procedure number 11 or procedure number 12, which deals with engine starting anomalies. There is going to be a procedure in which you are going to put a gauge at the pump discharge only, your high pressure pump discharge, and you are then going to use your motor capacity, your crank, your starter test, whatever you guys refer to it as on your particular aircraft. You're going to crank the engine up to 15% deadheaded against the fuel shutoff valve. And the pump has got to be delivering, if it's operating normally, has got to be delivering a specific procedure. We see that procedure on both the 399 and 400 series pumps is going to be about 300 psi. Anything less than that, either your pump has failed or it has lost capacity, and this could be contributing or may be the source of your problem for whatever your fuel system or engine operational anomaly is. So there is a procedure basically to look at the bottom end of the pump when the engine physically can't be started. Now, coming out of the fuel control unit, I should see a range of approximately 125 psi at the jump, that will ramp up to about 600 psi discharge pressure on the on high power situations. Now, the 125 is significant, and I'm going to get a little deep in the weeds here. At the discharge of the fuel control unit, there is a device called the pressurizing valve housing. And it is nothing more than a preset spring-loaded piston whose job is to maintain a minimum working pressure inside the fuel control unit of at least 125 psi. Now, it's not a regulator. We get into deeper detail into failure modes with this housing as we go through our line maintenance training. Needless to say, it will remain closed until pressure on the top of the piston gets to at least 125 psi. Then it just opens. So it's not a regulator or a metering valve or anything like that. So once pressure gets to 125, boom, it opens and fuel flows out to the engine. So the initial discharge I would expect then would be the set point or the crack point of that pressurizing valve housing, which is 125 psi. At max power, max speed, etc., I would expect to see pressures up around 600 psi. Now, one of the other things, if you gentlemen don't, or if you folks don't mind me going back just a little bit here, I wanted to talk about one item. going back to where we measure. Now, you could, again, I'm kind of backtracking, and I apologize for doing this. I skipped over this. It's my fault. You'll notice that this would be the typical gauge array that you guys would be looking at if you were to measure across all the big boxes. All right, we talked about this before. Now, notice in this graphic, I have the same gauge array, but I've removed the fuel flow or the fuel pressure going into the flow divider. Again, going back to my previous example, the fuel shutoff valve normally does not provide any kind of restriction. It's an open close. If it is restricting, there's something wrong with it. So, and because of the difficulty in trying to plumb a gauge into the flow divider inlet, you could conceivably leave it off of your troubleshooting list, because I would expect fuel control discharge pressure and flow divider inlet pressure to be the same, provided the fuel shutoff valve is not malfunctioning. Obviously, if the fuel shutoff valve is malfunctioning, I still have 2 gauges downstream that would be affected by that type of restriction. So the necessity for a flow divider inlet pressure gauge the necessity is decreased or even eliminated because of that fact. All right, now the next pressures then we would be looking at is that when fuel flows into the flow divider, its first destination is going to be out to the primary supply line. So your initial fuel goes to your primary atomizers. They are orificed in such a way as to create quality spray and pressure at low flow and low pressure. And so this is what gets you your initial combustion and your good initial early acceleration. Now, through an integrated orifice inside the flow divider, there is going to be a pressure drop that's generated before the fuel is physically supplied to the primary atomizers. Initial fuel introduction into your primary should start at around 85 psi at about 70 pounds per hour of fuel flow. And that's enough to get good atomization, quality spray for your initial combustion and your initial acceleration. Whether this is the duplex or simplex nozzles, it doesn't matter. And then the engine, as I ramp up, my fuel pressure can ramp up as high as 500 psi when I'm operating at max power, max pressure in the combustion chamber, max flow. My secondaries do not come in at the same time of the primary. That's what the flow divider is. It's a hydraulic sequencing valve that delays the introduction of the secondaries until I get a higher pressure and higher flow, because the secondaries are orificed in such a way as to create quality spray, but at a higher pressure, higher flow. So depending upon which your engine model is, your secondaries will be introduced around 35 to 40% RPM during an engine start, or 50 to 55% during an engine start itself. So obviously your fuel has ramped up in pressure coming into the flow divider, so that when the secondaries are allowed to flow, the initial pressure introduction is going to be much higher than it was for the initial primaries. And then from that point on, now I'm flowing primaries and secondaries, and that is a function or a characteristic of the 331. We do not throttle back. We do not shut off the primaries once the fire is lit. The engine, when it's delivering maximum power, is delivering fuel through all your primaries and all your secondaries. So the primaries, once flowing, never shut off. So you're looking at a ramp up from that point on to, again, about 500 psi, also in the secondary manifold. Now, typically, if I have a problem in the area of my primaries, we could usually attribute this as a decrease in flow caused by the fuel nozzles becoming contaminated. We try to avoid that through our manifold purging and all of our shutdown protocols that we do on the TPE331. But inevitably, over time, the nozzles will become gradually contaminated. We hope it's gradually contaminated. The end result can be a lot of those symptoms we showed you at the beginning of the program, to where the fuel is being restricted going into the combustion chamber. So if you're not delivering it to the combustion chamber, it cannot be used for useful power. Now, what we would typically tend to see on that would not be a low pressure at the primary secondary gauges, but an elevation in my pressure as the flow becomes more restrictive. Flow goes down, pressure goes up. Okay? Now, with the 331, if we refer to 720000 adjustment and test, or testing on later model revisions or later year revisions or current revisions, they're now renaming the adjustment test section into just testing. Under this, under the engine functional checks, you're going to find an item called the dynamic pressure test. Okay, this is a running check of your fuel, of your primary and secondary nozzle pressures. All right. Now, this test is becoming passé or redundant, if you will, in the fact that it does require a lot more man hours. It also requires, here's the other negative on this, is that you can't just go out and do a dynamic flow check off the jump, because you have no baseline to then compare your current numbers from what the nozzles look like when they were fresh and clean. So this is, so to be able to do this, to be able to use this check to determine the health of your nozzles, you would have had to have done this check when you did your periodic nozzle change interval. So a fresh set of clean and flowed nozzles, you would do this check to give you your baseline, so that down the line, if you suspect your fuel nozzles were giving you a fit, then you could do this check again and compare the two sets of nozzles. Now you'll note that what basically you're going to need 3 gauges, a primary, a secondary, and a P3 gauge. And what you'll do then is you'll run the engine at a series of fuel flows along the bottom here. And if the engine can't make takeoff power, you're going to run it to as high a fuel flow as the restriction will let you. You'll then read your primary and secondary pressures, subtract P3 from that to give you a manifold differential. And then you compare that, you'll plot those numbers along the respective lines. And again, you'll see criteria up here for if that differential deviates more than a certain number of PSID from your baseline, then your nozzles would require replacement. Now, another reason why this has become passé or become more of a unnecessary procedure is that with recent changes to the periodic intervals of nozzle of your simplex and duplex nozzle changes for flows and cleanings, it's now become frequent enough to where you generally catch your nozzle health going or deteriorating. You change the nozzles well before it gets to a point where you may start to see issues with your engine performance or having fuel system problems. Not saying that's a perfect statement, but it's pretty close. Okay. But if if you happen to be having an issue and you have a set of nozzles on there, even without doing a flow check, what a lot of operators will do is that if they look at their nozzles and they're coming up, they have a high time set of nozzles, so they're on the opposite side of, say, their half life, they may arbitrarily simply change the fuel nozzles as a way of a quick and dirty troubleshooting to basically see if that makes any improvement onto their fuel system or not. But as I say, generally with the current intervals of your fuel nozzle changes, both on the simplex and the duplex recently was just decreased by service bulletin to 350 hours. I remember in days when that was 600 hours that you were running nozzles up to. So there's been some changes in the periodicity on that to where it's now being changed at a frequent enough interval to where nozzle contamination, unless you've happen to get a dirty slug of fuel or are not adhering to Honeywell's engine shutdown practices, things like this, high cycles, things like this, your nozzle change intervals should be frequent enough to where you should be able to avoid the problem of clogged nozzles. Same thing with always charging your fuel manifold purge kit, etc. So I could go into all those rules and restrictions. Now, to put this together, let's say you have an anomaly. For whatever reason, I don't know why this is, but in my experience, people tend to knee-jerk a fuel system problem as the fuel control unit. It's always the carburetor. Nope, it's got to be the carburetor. Why? Well, in some cases, it's because they don't understand how the thing physically works and what its capacities and its limitations are. Others think that, oh, it's complex. These aircraft fuel controls are very complex, and so complexity breeds delicacy, and so it's the most likely thing to fail. In some cases, you may be correct to where a fuel control replacement is your only alternative or your final alternative. But in the cheapest and easiest to hardest and most expensive theory, if you will, you would probably want to look at that as the last end. And so doing a little bit of extra troubleshooting, throwing some gauges on and becoming more and more specific may save you a lot of time and a lot of money. For example, knowing what we've just discussed, let's say I had this situation. Okay, I don't need to see numbers. I can just look at them as that the parameters are within the normal range, they're not within the normal range. So I'm running into a problem, one of the problems we described earlier. Okay, let's say the engine's not making proper output power for the day. So I plug my gauges in as appropriate, and I run the engine up to as much power as I can get out of the motor, and I look at my gauges. Here I see that my fuel pump discharge pressure should be around 300 to 800 psi, looking good. It's normal. My fuel control discharge pressure is between 125 to 600 psi, right around 600 psi, let's say, on the discharge at that power level. That also would be considered normal by the numbers I've just recently given you. However, we look at our fuel, our pressures in the primary and secondary line, and we find them below normal. So obviously somewhere the pressure is getting out of the FCU, but it's physically not making it to the nozzles and manifolds. Well, in this case, the problem could either be a restriction in my fuel shutoff valve, potentially, or some failure in my flow divider that is restricting fuel out to the primary and secondary atomizers. In an instant like this, a knee-jerk FCU change would have resulted in no improvement in your situation, and the expenditure of a large number of man hours, as well as the cost of the component itself. So for what may have been an extra 45 minutes to an hour of troubleshooting saves you a huge amount of time. And so once again, reinforces that the theory that, you know, try to do your troubleshooting from the cheapest and easiest to the hardest and most expensive. Now, gentlemen, I hope you enjoyed this presentation. I hope you found it at least entertaining. Anyway, I hope, and maybe even gleaned a kernel or two, a little nugget or two. That would make me happy. Guys, if you are operating the 331 and are having some problems with this, don't hesitate to contact me. I offer my advice. Sometimes you may like it, sometimes you may not like it. But I offer my advice for free at any time, no matter what time zone you are. My phone never goes off. I again have up there on the screen, you have my contact information, and don't hesitate that if you'd like to bounce an idea off me or having a problem. I do not charge for this. This is free of charge, cheerfully offered. And so if you are having an issue with your engines, by all means, please pop me an email or give me a shout on the phone, and let's talk about what may be the issue, whether it's a fuel system problem, engine performance problems, whatever. Hopefully I can maybe give you some guidance or some direction that may benefit getting your aircraft and your engine back into proper service. Again, I want to thank Concord Battery and Virtualis Live for allowing me to present to you. I would like to also, again, if you are interested in training on the 331 family of engines, that you have my contact information. Please contact me at your leisure. I can provide you with quotes and also offer you training alternatives. We do everything from familiarizations, basic line servicing, line maintenance. We also do training on major periodic inspections, hot section, gearbox, compressor zone inspections on the TPE331 family of engines. And as I said, we offer flat rate pricing. Also, TAE is the only training provider that also offers customers what we refer to as engine aircraft specific training. Most of the other training providers offer you a generic overall TPE331, which doesn't get necessarily specific to your particular engine model on your particular specific aircraft. And so it's incumbent on you to then wade through what is pertinent to your application and what is irrelevant to somebody else's application. We offer training courses in which even the training material and the presentation is geared only to the engine models on that particular brand of aircraft. So if you have a Metro 3, I'm going to give you a Dash 11 class, and I'm not going to discuss the 5 or the 10T on a Commander or on or Mitsubishi or the Dash 8 Cessna Conquest, whatever that may be. You're getting targeted information. So I look forward to speaking with some of you, and also hearing your comments and everything on the presentation. I hope that the new year finds you well, and I thank you all for taking the time to listen to my presentation, and wish you all the best. Thank you very much.